Okay, we're recording.
Great, so I'm ready to start. Are we good to start?
Yes.
Okay, sweet. So hello, everyone. This is our capstone design project for Mech Design 2. We are group 11, and our product is called Hyperion. And I'll let everyone introduce themselves before we kind of get into this.
I'm Connor Bowman.
I'm Emily Briscoe.
Mia Fetty.
Hi, I'm Colby Ross.
Nolan Testa.
And I'm Joshua Valdivia. So I'll first start off with an outline of what we're going to be talking about. So we'll quickly do a product overview, kind of go over the summary and the dimensions of it. And then we'll get into the reflector subsystem, the actuation, the electronics, the structure, and then finally finish up with the conclusion. And then for each of the subsystems, we're going to go over a little bit of the analysis and kind of what was needed from the customers on and why these systems kind of exist. So for our Hedgehog concept, Hyperion focused mainly on simplicity and reducing cost. The main thing that we do this by is through our actuation method. We use low-cost pneumatic actuators and pumps and solenoids to kind of control the pneumatic actuation. Majority is OTS parts, and we meet our customer needs. Kind of what we're best at is being resourceful and being good at manufacturing. We are passionate about providing clean energy at competitive prices. And finally, what drives our economic engine is curiosity to invent, and innovate drives our economic engine. Yeah, so the product overview. So summary, right now we have it as 6 reflectors per module, using, like I said, pneumatic linear actuators to move these reflectors, 2 pneumatic actuators for each reflector, and solenoids to control those pneumatic actuators. And we have a custom PCB with linear sensors to measure the precision and how much these linear actuators are moving. With the concrete base, which is just kind of, for now, these can also be mounted into the ground, and then a max system height of 0.4 meters. So I'll let Gio get into the reflector customer needs.
So some of the customer needs for the reflector are, well, overall, the whole heliostat module was supposed to be less than $100 per meter squared of reflective area. It needs to provide greater than 1 megawatt of solar energy. It needs to be a washable surface. Reflection area needs to be less than or equal to 1 meter squared, and our heliostat module actually is around 1 meter squared. Well, actually, exactly. It needs a solar concentration ratio of greater than 1,000 suns, and the operational lifetime needs to be greater than 20 years. And there you can see the features for all of these customer needs and how they were met. And I can explain that next on the next slide a little bit better. So an overview of our entire reflector is that it's a flat borosilicate flow glass around 1 millimeter thickness, aluminum reflective coating, and then which is the part that basically essentially reflects the light through the glass. We have also a protective coating that helps with the washability of the surface and protecting it from all the damage that can be found, for example, in a desert like sand. We also are using a Sozin 670 silicone adhesive that I'll talk a little bit more about later. And as you can see here, we have 6 total reflectors. Each one is about 0.1666 meters squared, and it's mounted to an aluminum supporting plate using that adhesive that I mentioned. So for the solar energy needing to be greater than 1 megawatt for 1 hour of the day, I calculated this based on how many heliostat modules we would need based on like how the reflector would work in our design. So Nevada absorbs around 5.50 kilowatts per meter squared per day. And I use that number using a reflectivity of around 93.6%, which is around the reflectivity that we found for borosilicate glass with aluminum reflectivity. And here, as you can see, the calculations we did, we end up getting about around 2,331 heliostat modules would be needed to reach that customer need. And these are perfect conditions. So this number would essentially be higher, and we could do further calculations. It's a little difficult because there's a lot of factors that come into play for this solar energy of 1 megawatt. Because, for example, the sun moves throughout the day. So then you can see there the sun path diagram. And that's going to change the angles and the percentages of actual solar energy that's reflected. And it also depends on the time of day, the strength of the sun. So there's a lot of factors that come into play to determine the actual number of heliostat modules necessary. So the solar concentration ratio of greater than 1,000 suns, because each reflector is about 1/6 of a meter squared, and in total, that's a total reflective area of 1 meter squared. I calculated that that's around a ratio of 1:1, but then I used the reflectivity of 93.6% to get a ratio of 1.068, and I calculated that 1,068 heliostat modules would be needed to reach that solar concentration ratio of 1,000 suns. And on the next slide, we talk a little bit about thermal fatigue resistance. And that's the main reason that we chose the borosilicate glass over the soda lime glass, because of the thermal fatigue resistance that borosilicate glass has. The coefficient of thermal expansion is about half of that of soda lime glass. So the higher the number in this case, the better for the thermal fatigue resistance. And like I said, that's one of the main reasons we chose it, as it has a very similar reflectivity as soda lime glass. It is a little more expensive, but we think that it's needed to meet that customer need of lasting at least 20 years. And then here's the thermal stress as well, as you can see. And when we compared that thermal stress that we calculated, it was much, much lower than the fracture stress. So we found that that was going to be okay for our design. So the cost, we calculated that with the glass and the aluminum reflective coating, it was around $6 per module. The protective coating was going to cost around 26 cents per module. The sealant, the mirror adhesive, was around 39 cents, and the aluminum sheet metal would be around $1. So the total cost for the reflector portion of our heliostat was going to be around $7.65 per module.
Great, thank you, Gio. And then I'll talk about the actuation a little bit. And then, so for the customer needs, again, for the overall system, costs need to be less than $100 per meter squared. Be able to withstand the environment of Las Vegas, have to be able to redirect the sunlight, track the sun within an error of 0.25 degrees, and then have an operational lifetime of greater than 20 years. So to talk about this, so I'm going to talk, so for the actuation, like I said, two pneumatic linear actuators, 12 per module, because it 2 for every 6 2 and then 6 reflectors. And then we have binary solenoids that are turned off and on that we're able to push pressure to these pneumatic actuators, but we can select which one we're moving by opening and closing the solenoid valves. So if we wanted to move 1 out of the 12, we can close 11 of them and just open one of the solenoids. And then the flow is controlled with one central pump for 17 to 18 modules to kind of decrease that cost. Yeah, and then it is extremely low cost at the pneumatic actuators being only $3 a piece, and the solenoids being less than 50 cents. And then the other thing, the main concern with this design would be kind of solar tracking. So we did a little bit of calculations, kind of looking at like doing vector transformations, being able to decide what kind of our center post height would be and what length of our linear actuators needed to be in comparison, to kind of figure out what our max and minimum angles are going to be. What our max angle and minimum angle we needed a range of 50 degrees, which is that value. It's going to be 15 degrees plus the latitude of Las Vegas, which is about 35 degrees. So yeah, so by doing this, we're able to track the sun throughout the entire day. And then this can be, this could also be changed for different locations. And then I'll also hand this off over to Emily to kind of finish up the actuation.
Apologies for that. Here we have our actuation analysis continued. So assuming minimal pressure loss due to pipe friction, and we have a pump pressure of 80 megapascals supplied. I just did a quick calculation here. We have 17 modules per pump. And with there being 6 mirrors a module and 2 actuators per mirror, we end up with 204 actuators per pump. And so we end up with an actuation pressure of 0.392 megapascals. Next slide. And then continuing this, I found the, in like the worst case scenario where the actuator has to hold up the entire reflector weight, we end up with a required pressure of 0.0512 megapascals. That's just to hold it up, so we have to surpass that. But as calculated previously, the pressure supplied is greater than this. And it also falls into the linear actuator service range, which is 0.1 to 0.7 megapascals. And this could vary depending on how many pumps are active at the same time. And next slide. And then finally, we have the cost for the actuator. So we ended up choosing this actuation system because it ended up being cheaper than some alternatives we had, such as like stepper motors and then some of the DC motors. So with the electric hydraulic pump split between 17 modules, we end up with $17.65 a module. And then for the linear actuators, those were pretty cheap. So $270 each, and with 2 per mirror and so on and so forth, we have $32.40 a module. And then the solenoid valves, those actually control the fluid flow into the actuator. And I think Ria goes on about that a bit later. Those are 10 cents each, and they're $1.20 a module. So it ends up with a total actuation cost of about $51.25 a module. And next slide. And I'll just hand it off here to Ria.
For the electronics, the overall cost of everything needs to be under $100, and the electronics, the entire subsystem costs about $21.5. Each module must mitigate optical losses due to tracking error, and for that, we have optical sensors to track the position of our actuators and a controls algorithm to minimize this error. The sun tracking must be automated, and we have a microcontroller with a Wi-Fi module, and individual parts must be less expensive than OTS parts, and our custom PCB is cheaper than an Arduino Uno, which would be our comparable option. Next slide. Our custom PCB will have 12 GPIO pins, 12 ADC pins, and a 2.4 gigahertz Wi-Fi module, which is common for IoT devices. We need 12 GPIO pins for the 12 solenoid valves and 12 ADC pins for the 12 sensors that we have. Our electronics housing is made out of PPE and it's sealed, and the hole is actually for the wires. Next slide. So to determine if we need any extra methods of cooling the electronics, I did a heat transfer analysis. The maximum operating temperature of the chip is actually 80 degrees Celsius. Our power consumption is 30 milliwatts. Our max air temperature for Nevada is about 45 degrees Celsius. And using free convection and radiation, our chip surface temperature, which is also assumed to be the max temperature because of how thin the chip is about 68 degrees Celsius. And free convection was calculated to actually be very negligible. Next slide. For our automation, how it's going to work is that we're going to have a central tower that's publishing to a server. What it's publishing is actually desired elevation and azimuth position or angles. And each microcontroller, which is specific for the module, will filter for its module specific data. We'll actuate the solenoid valve until we reach the desired position, and we'll maintain this position. And each heliostat, so individual mirror, can actually move on its own because each of the valves will have its own instance timer. So for the sensors that we're going to be using for our controller, we're using optical distance sensor, which is utilizing lasers. Next slide. For our controller, we actually have a multiple input, multiple output system, but because we can move each degree of freedom separately for the mirror, we can approximate it as 2 single input, single output system so one for azimuth and one for elevation angle. We have a 3 degree of freedom system, but we approximated it to 2 degrees of freedom because that's all we care about. So as an overview for the controller, we're controlling the solenoid valve, but we're measuring the actuator displacement. And where our input and output is our elevation and azimuth angle. Next slide. We did a dynamics analysis to see what our controller needs to look like. So this is specifically for the elevation controller. where both actuators will move in the same direction, so they can be assumed to sum to one actuator. The U-joint is assumed to have 1 degree of freedom, so acting almost like a hinge. And the friction and other forces are negligible, or at least not counted for this analysis. Next slide. So from our differential equation of motions, as you can see over there, we have theta inside of our differential equations of motion, one of our differential equations. So theta is our command. Our command variable is in the differential equation of motions, as I said, and that's what tells us that we need a feed-forward term. Next slide. The idea is almost the same with the Azimuth controller. The only difference is that instead of, well, we're measuring a different angle, but instead of summing the two actuators, they're working in opposite directions, but equal displacement. So if I wanted to move the mirror a certain direction, I move both actuators the same amount of displacement, however, with different directions. Next slide. It's the same idea. Our input variable, our command variable, is basically in our differential equation. So we need a feed-forward term. Next slide.
Hey, good morning. This is a quick block diagram of our PID controller with a feed-forward augmentation. As you can see here, we're taking a input. This is for modeling of one of the actuators. The second actuator will be a duplicate of this block diagram, but we're taking in a desired that translates into a desired angle, velocity, and acceleration, putting into the feed-forward dynamical model of the heliostat model. We can use this to predict the command output going into the plant. So this is fed back into the PID controller gains before going into the plant, which is a manipulator Jacobian, a 2x2 matrix of partial derivatives that act as a endpoint displacement in respects to the elevation and azimuth angle. This is important to formulate the control terms for the end reflector or the end effector instead of the joint angle errors, so that if we know the desired end effector position of the heliostat or the reflector, then we will know the desired angles within that heliostat will be. So this is done using some trig embedded into the partial derivatives to get our desired and actual output into the heliostat. Next slide.
The total cost of the electronics is $21.5. The custom PCB was approximated to be about $5 per module, and that also includes hiring a contractor for a week to design it. The electronics housing would be 50 cents. The hardware, which would be for the electronics housing, and also the wiring and to seal the housing, is about $4 per module, and the distance sensors were $1 each, so $12 per module. Next slide.
So here we have the customer needs for the support structure. The cost has to be less than $100 per meter squared for the whole system. The support structure is at $53.55. It has to operate in the ambient conditions of Las Vegas, Nevada, and we can do that. It can withstand temperatures from 30 to 111 degrees Fahrenheit and wind speeds up to 90 miles per hour. The modules must redirect sunlight to receive or target on a tower 100 meters tall, and our support structure allows for rotation of 180 degrees. The total module area to reflective area should be small. Our reflective area ratio is 2.25, but we could decrease the amount of concrete we have per module, but we didn't think that the 2.25 ratio was that much of an issue, so we left it. The individual parts must be equal or less expensive than OTS parts, and that's exactly what we have. Most of our products, or most of our components, are OTS parts. And then the operational lifetime must be greater than or equal to 20 years. Our factor of safety was 2.09, and all of our components are steel and will be able to last out there in the conditions. So here we have the overview of it. The structure is supported in a concrete base. There's a single steel tube that is attached to our U-joint, which allows for the movement. The U-joint is then attached to a bracket, which is attached to a thin steel sheet, which our reflectors are going to be adhesed to. And then the support structure was designed to be as simple as possible with mainly OTS parts to reduce our total cost. Here we have our factor of safety calculation. So the force we calculated there was the wind force at the worst possible conditions. Then we did the bending stress calculation, and we got that with the steel pipe that our factor of safety is 2.09, which exceeds the customer needs of 2. And on the next slide, we have the cost. So there's the breakdown of all of the components as well as the fasteners that we need to make our support structure works. And it comes out to $53.55 per module. And then I'll hand this over to Connor.
Yeah, thank you. So I'll kind of carry us to the end of this presentation, kind of going over a top level summary and the CAD models of the design. Here we have the CAD rendering of the full design with all 6 mirrors. As you can see, we have most of our hydraulic lines stored underground to protect them from the elements. And each mirror is individually controlled, which you can see on the next rendering that we have. Here is an individual mirror. We have the actuators pivoting around the U-joint and the mirrors attached to that steel sheet. And in those black boxes on the actuators are the sensors that we use for linear action. The next slide, we have simply an exploded view of this design with all the fasteners and such like that to kind of show the assembly of everything. Yeah. So overall, our cost is very much OTS limited. We have our total cost comes out to $170, which does not meet customer needs. But we just believe that this design can be kind of optimized with further negotiation with OTS dealers. On the next slide, kind of the summary. I kind of approach this design from a standpoint of trying to be as simple as possible. When trying to think of a new way to actuate things, we found that traditional actuation methods such as separate motors were not very conceivable and applicable and possible within the customer constraints. So we use these hydraulic pneumatics to actuate our mirrors, and we use a high precision PID control system for you to control where the hydraulics are using optical sensors. Another part of our design philosophy is trying to use as much amount of OTS parts as possible to reduce the manufacturing cost. But this is kind of a double-edged sword because we couldn't really find some OTS parts that were cheap enough to fit within our budget. However, because we kind of rely on a lot of OTS parts, the scalability of this design is very promising because we only have a couple parts and the parts are not very complicated and it can simply be made on the water jet or on a manual mill. On the next slide, we have our conclusion. So we believe this novel idea of using hydraulics to move these mirrors can be kind of leading the way in reducing overall operation cost for these energy plants. And the reduced cost, enhanced service life, and reliability of this design can reach the consumer goal of 5 cents per kilowatt hour. And that is our design. Thank you.
Okay, so again, I would like to encourage our external guests to go first if they have any questions, and then I will back clean up. And for this presentation, we had more time scheduled, so we have about a half an hour.
Okay, so this is Rick Miles with Northrop Grumman. I do appreciate realizing how expensive the stepper motors are and looking at a different approach in order to drive your costs down. Everybody else seems to be stuck on the stepper motor approach, and I understand that from a tracking standpoint, it's nice and controllable. But I like the different approach here. But with that, so you talked about the concrete. that you were going to pour, and then you're going to attach things through the concrete. I was having a tough time understanding where the pumps were going to be located with regards to your concrete pads, because I think you said that each pump was going to run 17 modules.
That is correct. Yes.
Okay, so is the idea that these pumps are going to be separate from the concrete pad? I'm just having a tough time picturing exactly when you actually go to install this out in Nevada, where are the pumps going to be located?
Yeah, they'd be completely separate from the pad. Just they could be underground or like in like a housing central, like in the middle of all the other modules, and just all these like as many lines as possible connecting to that one pump, and just being able to actuate all of those modules.
Okay, and then when you're dealing with hydraulics and pneumatics, typically you're going to have to set some sort of servicing schedule based on how much they're being actuated and that sort of thing. So
Okay.
just something you're probably going to need to consider is how you're going to go about servicing the pumps to make sure, because you're going to have them break down from time to time. You're going to have solenoids tend to be sticky a lot of times, so just some concerns that you might have down the line from a maintenance standpoint.
Okay.
And when you talk about your overall cost, that is per module. So like one of the things, so like your cost of your pump, do you divide that among 17 modules? How do you
Yes.
split it up?
We do that. Yeah, that's how we split up the cost. Yeah. So we'd
Okay.
have, yeah. I think one of our issues is that I think the pump is one of our one of our main cost drivers. And I genuinely believe it's because we couldn't find like an industrial level pump online, and find that pricing or get a quote on it. But yeah.
Okay, and then you talked a little bit about your choice of your glass and your reflective film was based on thermal fatigue. I'm just curious as to how much different it seems to me that you wouldn't have that much of a delta between the thermal fatigue of the different materials that you're looking at for the particular temperature range that you're going to be exposed to.
Yeah, I can talk a little bit about that. Do you mind going to that slide, Josh? A little down. I'm sorry, up. So, okay, so we went with the borosilicate glass. Really, the biggest factor here, we found that the coefficient of thermal expansion is a factor of 2 less than the most common soda lime glass, and it's a third less than some other leading manufacturing glass out there. And looking into the biggest differential temperature found in the Mojave Desert, we found last year, it was in June, it was about 55 degrees differential temperature from the morning into the evening. And we played that into the factor of soda lime glass, and we found that the expansion would be about twice that of the borosilicate glass. That's why the borosilicate glasses tend to be more used in cookware and things like that. The stress wasn't as negated, very minimal compared to the fracture stress, but we really wanted to think through the expansion of all the layers that comprise of the reflector. So you got the glass, you got the adhesives, you got the silicone, and all those are going to be expanding as the temperature rises and falls throughout the day. So the application is essential for the silicon to make sure it's very controlled, indefinite, and the glass itself was the biggest concern when dealing with the fatigue, is because that's directly exposed to the sunlight and the heat flux coming in, and then beneath that everything else is kind of shielded by the aluminum coating. So that was our main focus there. We found that the soda lime glass that's commonly used, it does deteriorate over time because of the thermal fatigue, expanding, contracting, cold temperatures, hot temperatures. It breaks down the aluminum coating and potentially the silicon holding everything in place. So
Okay.
that's why we went with that.
No, that's good. I appreciate the explanation. And then my last question, if you could go to where you calculate your support factor of safety. All right, so I'm I love free bodies so that I can understand what's going on here. I'm having a tough time picturing here with your analysis how you're applying the load and what sort of condition you're saying is your critical condition in order to calculate this factor of safety.
Okay, I can explain that. So if you go to the model, yeah, right there. So we said that the critical load was the bottom of the single steel tube where it meets the concrete there, because it's the farthest distance from the mirror. And we said if the mirror was at a perpendicular location and then the wind was at the 90 mile per hour, the harshest load, we took the bending moment from that. So the total distance from there to there. And then I used that as my factor of safety, and that is my critical load because it was the farthest from it and it's a tube. So it's not as strong as a steel like rod.
Okay, so again, when you're providing structural analysis, you need a free body so that
Yes, sir.
the person looking at it understands exactly what it is that you're analyzing to. Because I thought that might be what you were doing, but I can't tell that just by looking at the equations. Because you just give me a force value, and I'm not sure where that force value is coming from.
We have that calculated in our appendix, which is a hidden slide, but he can go and show you that.
Yeah, no, I mean, I don't need to see. I'm just saying
Okay.
when you present to people, right?
Yes, sir.
The key thing to any structural analysis, always start with free bodies.
Yes, sir.
Right.
That makes sense.
One of the things I did appreciate here, and Tom Singer's not available to watch these presentations today, but he's a finite element guy, and he always hates when people do finite element analysis on very simple stuff. And I do appreciate here that you did hand calculations because your loading's very, very straightforward. So good job on that. And overall, I thought you did a really good job with the presentation as a group. And I like the unique approach compared to other groups. So appreciate it. Thanks, guys.
Thank you so much.
Thank you.
Thank you.
Thank you.
Hey team, I'll jump in now. So can you take me back to the overall cost slide, please? Oh, wait, there you go. Okay, first off, when you say manufacturing and assembly, that's the labor costs, I'm assuming?
Correct.
Oh, thank you. Please always, and I know the panel is tired of hearing me harp on this, but I'm going to harp on it again. Thank you for including labor costs. That is a big thing that we see missing from a lot of presentations, and it can start to add up over time. So definitely always make sure you include labor costs, manufacturing, assembly, the whole 9 yards. I would be a little questionable how you did get $3 for assembly and manufacturing. That seems quite low. So if you can speak on that a little bit, I would appreciate it. I know no one wants to talk about
Okay.
costs.
I'll take it. So, like we said, a lot of our parts are off the shelf, so that kind of drives our manufacturing costs lower. And like very few parts are actually, I think, literally just the brackets on like these brackets at the bottom here are the only ones that that need to get manufactured. Everything else, it's just cutting glass and stuff like that.
Mhm.
It's not, they're very simple processes. Nothing needs to be CNC'd or anything. It's all manual. Yeah,
So wait, oh, go back to, you just went,
sorry.
no, the other way. There was
Okay.
like a slide with all types of bits and pieces everywhere.
Oh, yes. Oh, man.
Sorry, I am not an engineer, so
Right
that's
here.
gonna
No,
be
that's
my
fine.
description.
Yeah,
So are those, I'm assuming those are screws and things that need to be drilled in and assembled into the unit.
correct.
Okay, how long does it take someone to do that?
We didn't calculate the time, to be honest with you.
Okay, that's fine. Look, telling me you don't know is an okay answer.
Yeah.
It's something to go back and think about.
Yeah.
I would just say, you know, even if you were going someone who's minimum wage, which I would think
Yeah.
you would want someone above a minimum wage, because
Yeah.
honestly, I don't understand half the parts I'm looking at. I know they need to be screwed in somewhere. You know, that's going to cost some time for assembly.
Yeah.
And then I think Dr. Chesney had a great point in the excuse me, chat here. You know, underground lines and assembly is just $3 per module.
Yeah, that's probably something we need to take a closer look at.
Right.
Yeah.
So I really, really, really greatly appreciate that you guys kind of started, you know, saying, okay, let's start and figure out, you know, you recognize that you will need those costs. But do a little bit more, you know, do a little bit more digging into it.
I think we need a like a better breakdown of it as well. Kind of,
Right.
Yeah.
So yeah, definitely look into that. Because I will tell you, as an investor, when I see your labor costs are such a small percentage of your overall thing, and then I see all these, you know, thingamajigs and do-wats and whatever, I'm not very confident.
Makes sense.
Then let's see. I want to thank you guys all who dressed up. You look professional. It really helps, you know, from a perspective side, and let's face it, lots of things are perspective. You know, that if y'all physically look like you have your act together, you dress nicely, you look like you're taking this seriously, you present, you know, you're sitting up, you present yourself like you're taking this seriously, then I actually think you're taking it seriously. So that helps me as an investor have a little bit more faith in y'all's product. So don't overlook little things like that. And thank you so much for all of y'all dressing up and looking nice and presentable for this.
Thank you.
Thank you.
Okay, so I guess that's my cue. And I have a couple questions. So my number one question is, what reality did you wake up to between slide submission and presentation where you realized that you were not going to meet that $100 goal?
Well, it actually happened when, so before, when we had a pump selected, there was actually an oversight where we realized that there wasn't any like actual motor like attached to that. So we ended up looking for a motor, and the motor ended up driving the price too high for that specific pump that we picked out. So then we had to look for an alternative pump that was cheaper. So it ended up quite nudging us over the $100 limit.
So you kind of designed the pneumatic air compressor rather than just full system off the shelf. And you forgot the key part to your air compressor was the motor driving it.
So these two parts like that she's talking about, the motor and the pump, are both off the shelf. It's just like I had said earlier, trying to find large vacuum and pressure pumps is very difficult to find for a large system like this. And yeah, it was just wrong pump essentially.
Okay.
Yeah.
Understandable. So as senior engineering students, you have not yet developed the type of contacts you would need to help get you the right thing. And you just, okay, well, good job catching it before you presented.
Yeah.
And a note about your resolution and being able to control it to the resolution you can read. Yeah, you have great reading resolution that you can tell to very high accuracy of what direction you're pointed in. Just want to warn you that, especially with solenoid, bang, bang control, essentially on, off, that don't expect to be able to actuate it within the degree that you can read. Let's see, anything else and great response to that. So thank you very much. And thank you especially for indulging us with the risk of chasing down a path that was kind of uncertain, but hopefully worth the risk and showing us something really unique.
Thank you.
Thank you.
With that, if there's no other questions, I'm going to stop recording and I'm going to leave, and typically we'll let you guys do a decompress, debrief yourselves on this channel. Thank you.
Thank you.
Thank you so
Thank
much.
you so much.
Thank you.